Welcome back to my YouTube channel. Now this video, we are going to investigate the mechanical energy by using the Newton cradle. So I have two mass of ball of equivalent mass. If I were to slow it down in slow motion, here you go, this is what will happen. All the momentum from first point will transfer to the second one, and then it will go up and come back down to minimum equilibrium, going out at kinetic energy to potential energy, kinetic and potential. This motion happens so fast that if it were to be normal speed, and I will show you shortly, it will look like this. So how are you going to measure the height? Now if I were to draw it and have a look for yourself, if it were to be the right hand side here, if this is the center of mass and this is the level at equilibrium, and if this is the maximum position, the increment of height is this much. I hope you can see it. This is actually h. So as when you come back down to minimum position here, and then it will be at maximum speed, like here. This is at maximum speed. This is where you have a V max. This is where you have your maximum kinetic energy. When it's at this height, you have the potential energy. Let's use U max, maximum potential energy. Here, this is where you have your maximum kinetic energy. Now the idea of the transfer of mgh to half mv squared as the essence of mechanical energy. I mean, this is what you mean by mechanical energy. We have all the potential energies fully converted into kinetic energy. But how do you use it in practical case scenario? How do you actually find out what's the speed down here? Or how are you going to find out what's the height in the first place? The height here is so small that it's almost invisible. If you don't even freeze it, you don't even notice there's an increase of height. Right? So, but what you see here is that the height is small, but the horizontal distance x is huge. This is something that we can measure. Then I believe, and it's definitely for sure, there's a relationship between h and the horizontal distance x. We need to find out what is their relationship so that we're able to calculate this speed. Right? Now, as you may be aware that this equation of mgh to kinetic energy, the mass can be actually cancelled out. The v of squared is actually 2gh, or the v is actually square root of 2gh. If I know the h, height, I will be able to find out what's the kinetic energy, v. I will know the speed here. So how do you find out this? Now to start out with, let me draw the diagram again, probably down here. I mean, you'll see the practicability of this, the logic behind of doing this video. I mean, the height is really small, you can't measure it, but I will be able to measure the x. So therefore, I need to find out what's the relationship between the h and x. Right? Now, if I were to redraw this diagram, probably here, it's my length of my wire, and then I draw another line, probably the red line, and then from here to here, I think it's somewhere around here, right, for approximation. Now, if I were to displace this pendulum bob by an angle theta, or I would say I would displace it by a very small angle. I would say the angle is roughly 1 to 2 degrees. Okay. So what happened is, I will form a triangle, isn't it? So eventually this is, whether the angle, magnitude of angle is not important here. The most important thing here is now form a rectangle, isn't it? I mean a triangle. And since this is L, this is the length of my bulb, the pendulum. So this is what I meant by the H, isn't it? This is the increase of height. So how am I going to find out? How am I going to measure it? You can't even measure it, it's too small. But of course you may use the software to measure it. But what's the relationship? Right? So this, therefore, I was able to find out this length here is actually, if I were to use a highlighter, I mean this length is actually L cos theta. Right? L cos theta. If you look at this triangle. And hence, my height, h, is equals to the length minus the length cos theta. The whole length, subtract this length, so I'll get the height. So if I were to factorize it, cos theta, and it seems like it's working now. I mean, I do not need to measure the h, but if I know the angle, but since the angle is small, but if the angle is small, then how am I going to measure it? You find it even hard. Or you may actually use a protractor. But an easier way is, relative to x, what's the relationship between the theta and x? Now, for small angle, theta, say, if it's a really small angle, this curved line appears to be a straight line, where both sides it's actually L or R. So if the curved length, or they call circumference, or this arc length, theta angle is the ratio of how far to the length, S over the length L, or we call radius. But I can't place it into here yet. Why? Because it's the cost of a radian. So what we can do now is to find out the relationship between theta and the x. So the theta, I will be able to, in calculus, we learn about this Taylor series of expansion for cosinus, where the cos theta in radian is actually equals to, it's a even number, where it is equals to 1 minus plus minus plus, you fill in the blank over something. Cos is an equal number, so it's 2 factorial, 4 factorial, 6 factorial, 8 factorial. We do not need to have so many terms. Okay? Then this is actually radian squared, radian power 4, radian power 6. You follow the number down there. And 8. You do not need to have so many terms. Actually, normally we use the first one or first 2 or first 3 terms. Okay? Now let me give you an example. How does it work? If you want to find out cos 0.5 of a radian, the angle would be what? No, let's use Siri. Hey Siri, what is cos 0.5 radian? Oh, Siri doesn't work while I'm doing the recording, I guess. So it crash, doesn't work. Right, so let's say I have cos 0.5 of a radian. It's 0.8 0.7758 ratio. Now if I were to use this number and substitute into here, then 1 minus 0.5 squared over 2 factorial plus 0.4 power 4 factorial, to your surprise, the answer would be 0.8776. So if you use only 3 to 4 decimal place, you get the same number. Okay, so this is how it works. So because of this, my H now is therefore equals to H times 1 subtract cos would be 1 minus, the angle is small, so I use the first two terms. That should be good enough already, right? And hence, therefore, this is equals to H multiply 1 and 1 to be gone. It's actually radian squared over 2, right? So it's very close there now. Now it's that, why is that H? It's not a H, sorry, I made a mistake. This is actually L. Finally realize it. Okay. So now, theta and H, when they with a small angle, theta is S over L. And this S is actually equivalent to X if the angle is small angle approximation. So hence, therefore, H would be L times half. Theta is actually X over L squared, right? Because of this effect, right? And then what you can do, simplify the L and the L. So therefore, my H is actually 1 over 2 x squared over L, or x squared over 2L. So this is my height. Now if I know the relation between then H and X already, then I will be able to substitute it into this equation earlier. So therefore, V is actually equals to square root 2G square root of the H. So square root of this will become x squared over 2L. So I square root it. So therefore, my V speed bringing to the front is x 2 times gravitational acceleration times 1 over 2L. And now 2 and 2 can be cancelled off further, and hence it's equals to x square root of g over L, right? So that's the speed. So if I know the horizontal displacement and I know the length that I use that can be easily measured, then I'll be able to find out what's the kinetic energy, equals to half mv squared. You can easily figure it out by this way. So that's all from me. Stay tuned for my next video.